Hello! In this video, we're going to prove the following theorem. Let A be an m by n matrix and let K and L be real numbers. Then, the matrix K plus L times A is equal to the matrix Ka plus La. Now, before we get into proving the theorem, let's remind ourselves of some definitions. Our definition of matrix addition is as follows. Let A and B be m by n matrices. We define the m by n matrix A plus B as follows. For each pair of integers I between 1 and m and j between 1 and n, the ij entry of A plus B will be equal to the ij entry of A plus the ij entry of B. So essentially we just add the corresponding entries of matrix A and matrix B together. That gives us matrix A plus B. Now, we also define scalar multiplication of a matrix as follows. Let A be an m by n matrix and let K be a real number. We define the m by n matrix Ka as follows. So for each pair of integers I between 1 and m and j between 1 and n, the ij entry of Ka will be equal to K times the ij entry of matrix A. So we just take each of the entries of matrix A, multiply them all by K, that'll give us the matrix Ka. Now we should also know what it means for two matrices to be equal. It means that they have the same corresponding entries. More precisely, it means the following. Let A and B be m by n matrices. Then A is equal to B if and only if, for every pair of integers I between 1 and m, j between 1 and n, we have that the ij entry of matrix A is equal to the ij entry of matrix B. Right? So it just means that they have the same corresponding entries. Okay, now let's look at the statement in the theorem. Notice, since A is an m by n matrix, and K plus L is a scalar, when we do K plus L times A, that will give us an m by n matrix. What about on the right-hand side? Well, if we take the m by n matrix A, multiply it by the scalar K, well then Ka is an m by n matrix. Similarly, La is an m by n matrix. And therefore their sum must also be an m by n matrix. So both the left-hand and right-hand side of this equation are m by n matrices. So to show that they're equal, what we want to do is we want to show that they have the same corresponding entries. So we want to prove for every pair of integers I between 1 and m and j between 1 and n, we have that the ij entry of this matrix is equal to the ij entry of this matrix. So, to prove that, since we're trying to prove a statement about all I and j, let's give ourselves arbitrary I and j. With this arbitrary pair of I and j, we want to show that the ij entries of these two matrices are equal. So let's start out by writing the ij entry of this matrix. So what can we do with this? Well, by definition of scalar multiplication, the ij entry of K plus L times A is equal to K plus L times the ij entry of matrix A. Right, so we can pull out the K plus L. That is what the definition of scalar multiplication tells us. But then from here, we're able to distribute the ij entry of A across the parentheses. So we just distribute it across, just like this. And the reason why we're allowed to do that is because all of these guys are just numbers, right? The entries of a matrix are real numbers, well, or complex numbers, whichever one you're working with. So we can distribute across this parentheses, and we get this. So then what can we do right here? Well, we can apply the definition of scalar multiplication again, because we see that K times the ij entry of matrix A is precisely the ij entry of matrix Ka. So essentially, we're just moving the K inside this parentheses. This is just the ij entry of matrix Ka. Similarly, we can move the L inside this parentheses. That's just the ij entry of matrix La. So really, we just get this. But then from here, remember the whole goal is to obtain the ij entry of matrix Ka plus La. So then at this point, we can just apply the definition of matrix addition, right? We're just adding the corresponding entries of matrix Ka and matrix La. So this is precisely the ij entry of matrix Ka plus La. And so that's it. What we have shown here is, given I and j, we have that the ij entry of this matrix is equal to the ij entry of this matrix. Since I and j were arbitrary, we have proven for all I and j, the ij entry of this matrix is equal to the ij entry of this matrix. But that's precisely what it means for these two matrices to be equal. And so we're done. This completes the proof. And so yeah, that's pretty much it for this video.